Okay, so yeah, let's move on to today's topic. So far we have discussed lots of the topics about the 3D reconstruction and also the generation as well. So NERF was kind of the state-of-the-art technique, which is about like 3D reconstruction from the multi-view images, and then we move on to the topics about like the few shot reconstruction and the zero shot reconstruction. So actually, the zero shot reconstruction is about basically 3D generation. And we also discuss some of the ideas in terms of like how we can utilize the pre-trained image diffusion models in a way that we can basically create some kind of the 3D shapes like this that you can see on the left-hand side using this core distillation, the sampling the idea, which is basically leveraging loss function of the diffusion model in a way that we can make some kind of 3D models that looks the plausible for all the different views. So that is all about like reconstruction degeneration. And today we are going to switch our gear in terms of like discussing more topics about the 3D processing. So basically we're gonna discuss some of the topics about the 3D processing in next couple of the weeks. So we basically discussed some of the ideas about like the point net, like all the variants of the point net, which was basically about like the some kind of networks that we can solve some kind of the classification and the segmentation the problems. And today we are going to discuss some of the ideas about the 3D object detection and the segmentation, which is very, the fundamental kind of the tasks in the many kind of the vision, the problems. For example, like obviously in the autonomous driving, basically detecting other the cars and also some other the objects like the pedestrians and trees, many kind of things will be very essential the tasks. So if you go to the Waymo the website, then you can actually check out there the open data set, which is basically provide some kind of the a sequence of some kind of a point cloud, which is basically describing some kind of the outdoor scenes with kind of many of the cars in a way that you can basically play with like solving some of the problems of like detecting some of the vehicles and also their trajectories as well in terms of solving some real problems in the autonomous driving. So 3D detection is basically the very fundamental task in the autonomous driving, and also in many other the robotics applications as well. In terms of when you basically train the neural net in a way to basically teach the autonomous agents in terms of like interacting with some kind of the real objects, basically detecting the objects and also segmenting them from the 3D kind of representation would be very the fundamental task. So I'm not going to play this video, but you can basically see then this kind of 3D object detection, this segmentation can be used to basically teach some robots to basically interact with some kind of the real scenes. And actually, not only for some kind of some robotics applications, let me just move on to even for some kind of a scene reconstruction, the object detection, the techniques can be used. Because while we also discuss some kind of the many other representations like the NERF or many other things, still some kind of some CAD representations for the 3D meshes might be the best representation for many the downstream applications for some kind of the high quality rendering and also some kind of physical simulation for many things. Like having some very high quality mesh might be really important things. And for that, basically, if we want to basically turn some kind of real scenes into some kind of the some CAD model scenes, the best way that we can make this kind of the CAD model scenes might be is that we are detecting many of the objects in the scenes and replacing each of the region with some kind of the CAD models of the objects that we have. So those are like all the examples that we are basically detecting some of the chairs, sofas, and the tables, many other things in these 3D scenes, and basically placing some of the CAD models that we have in terms of basically converting some kind of some scanned or the 3D scenes or some of the videos of the 3D scenes into some kind of the arrangement of the 3D CAD models in terms of like having some CAD representations for the scenes. And also for the many other applications, even in the medical imaging, for example, for this kind of 3D segmentation and the object detection, the techniques can be used to detect some kind of the organs or the tooth in this case. This kind of information can be used in the many kind of the some AI based some kind of the technologies to diagnose some kind of the disease or something. So as you can see, like 3D object detection and segmentation will be basically very fundamental tasks in the many applications. And the question is that how we can basically approach this kind of big problems. And for that, we are going to first see like particularly how people try to solve this problem for the 2D image case first. So this will be very quick overview for the 2D object detection and the segmentation, especially for some of the people who took the computer vision or some kind of the AI or deep learning courses. This might be very kind of the fundamental things. So actually, I'd like to ask like how many of you know these kind of the techniques like RCNN, fast RCNN. How many of you are basically familiar with this kind of the very old techniques? Type yes if you basically have heard about this kind of RCNN, fast RCNN before, or no if you have been not, yeah, hear about this kind of the old techniques. Yes or no, a little bit. It's kind of like half yes and half no, I guess. Yeah, so this is basically very kind of the fundamental the techniques in the deep learning the literature, which is also very kind of the old techniques compared to so many recent things that we also discuss in this course. So let me briefly review the ideas in this kind of the old work. So basically their goal is to basically detect some of the objects in the given image and also representing these kind of objects into the 2D bounding boxes. And the question is that how we can utilize some kind of the given some typical the convolution neural network in a way to basically find many of the objects in the image. And if we think about the typical neural net architecture, like the point net, so basically what we can do with the point net is that we can either predict some of the information per object or per point, right? So you implemented the two versions of the point net. One was the point net, the classification the network, and the other one was the point net, the segmentation the network, right? So the point net, the classification the network is the case that we are basically predicting the per object information, right? So we are basically getting some kind of the classification, the scores for the entire the objects in the image, right? And also we can either predict this kind of information per point. That was the case of like making the point net the segmentation the architecture. So for each of the point, we basically get some kind of the classification the scores, right? But this is none of these kind of the cases. So this is not the case that we are just getting the per image information and also not the per pixel information. Even we don't know how many of the objects we will be presenting in the given the image. So in this kind of the case, how we can basically utilize the given the convolutional neural net. So that's kind of the basic the problem here. So what people have tried to do is that basically people basically employ some of the so given some kind of the method, which is basically proposing some of the regions in the image. So basically, we are utilize some kind of the existing the algorithm, which is basically proposing many of the regions in the image. And then what we do is that we are treating each of the region as kind of the individual the image, and just like feeding them into the convolutional neural net in a way that we can basically get some kind of the classification discourse for each of the region. So this is the very basic the pipeline. And for each of the components, basically what we can do is that for the region proposal, the idea that people are using is this is basically this the selective search algorithm. So basically the idea of like this algorithm is that we are basically starting from some kind of the superpixels. The superpixels is basically nothing but basically having some kind of the small the clusters of the pixels that are basically sharing the same the colors. So it's kind of like some kind of the very small the clusters of the pixels over the entire the image. And what we do is that we are basically doing some kind of the hierarchical merging. And this is basically a task that we are doing without any kind of neural net. This is basically very simple the algorithm and also the non-learning based kind of the approach. So what we do is that given this kind of the small the clusters of all the pixels, we are basically checking all the adjacent the groups, the clusters of pixels, and check whether they also share the similar the colors or not. So based on some kind of the measure of the proximity of the two adjacent superpixels, we are hierarchically basically merging those kind of the pixels in a way that we are making some bigger and bigger the clusters. And then we are basically going up to the all the way up to basically having the one single the cluster, which is to be the case that we are having all the pixels in the image. And also in the all the intermediate the layers that we are basically making some kind of the merging of the all the superpixels, we're gonna have some kind of bigger the clusters in some kind of different sizes, right? So we are basically collecting all these some kind of intermediate the clusters of the pixels as kind of the proposals of some kind of the objects, the regions in the images. So if we basically take the bounding boxes for each of the region in the all the way of the going up to making the biggest the clusters, we're gonna have some all the intermediate clusters, and for each of them we're gonna get the bounding boxes, and those bounding boxes will become the region proposals that we're gonna check whether this each of the region is really representing a object or not for each of the images. So what we basically do is that once we basically collect all this kind of the region the proposals based on this kind of hierarchical merging the idea for each of the region, we are basically making the bounding box and the cropping the region and resizing all the boxes in a way that we have the some fixed size of the images for all the cases. And then we're just treating them as kind of the individual images and just feeding them into the convolutional neural net. And then we are basically getting some kind of the classification discourse for each of the region. So those are basically is a very simple the idea in terms of basically getting some kind of the objection, the detection the results. And can you guess what the kind of the downside of this kind of approach? If we have some kind of these three components, like having some kind of the region proposal, the first, and then cropping all these kind of the regions and just feeding them into the neural network to get the classification scores, what would be kind of the issues in the test time? Yeah, so it'll be yes, as you answered here, obviously the problem might be is that it'll be really slow. Actually, there are two reasons that why this will be slow. Like the first reason might be is that we are basically incorporating the reason proposal the algorithm, which is basically proposing the reasons in a kind of the hierarchical the merging the way, which means that it's kind of some kind of the iterative step. So we will need to basically iterate the hierarchical merging the multiple times in a way that we can get the regions in all the different scales. And this will basically take some time. And also the more the time consuming the part here is that we are basically making some kind of lots of some small images and then feeding them into the neural network, which means that even when we detect some kind of the objects, like single image, this will be the case that we are basically generating like 2,000 images to check whether each of the region the images are really basically somehow including some of the objects or not. So this is really the time consuming task. So people also thought about some kind of the ideas in terms like basically how we can boost this kind of the process. So the idea was basically the fast RCNN, which is basically reducing the computation time in a way that we are not basically feeding all the 2,000 images into the convolutional neural net. But here the idea is that we are just only feeding the input image into the neural network in a way that we can first get the feature map for the entire image. And then what we can do is that we can basically take the features for each of the region. So we are only taking the features of each of the pixels that are included for each of the region in a way that we are basically just getting the features for each of the region is in terms of kind of like doing some sort of the region pooling. So once we basically get the feature map for each of the region, then we can just use the very small neural network to predict all the outputs for each of the region. So this basically can save some time in terms like processing each of the region images, but we are basically first processing the entire image using a single neural net, getting the feature maps for the entire image first, and then just taking out some of the features that are corresponding to each of the region. In this way, we can basically save the time to process all the 2,000 images. So this was also kind of very simple, the idea in terms of like, we are taking out some of the some feature maps of each of the region using the single neural network. So which can basically save some time that we are processing the lots of images, but still the bottleneck basically lies in the part that we are basically getting some kind of region proposals. So as I said, like this is basically the process that we are basically running some kind of the hierarchical demerging of the regions, and that will basically take some time to get the all the proposals. So the next idea after this was basically how we can also basically save time for the region proposal. And basically the idea is that we are also using the neural network to propose the regions, not using some kind of the non-learning based some kind of the algorithms. So what we can do is that here the basic idea is that now for each of the some local the area for each of the pixel basically, we are basically getting this kind of the fixed set of the 9 some kind of the proposals for the regions, which will be called as kind of the anchor the boxes. So what we can do is that from the next slide here, for each of the pixel, we did have this kind of the 9 the fixed set of the predefined the bounding boxes, and these are called the anchor boxes. So we are basically having some kind of the 3 samples of the aspect ratios, and also the 3 samples of the scale. So by making all the combinations of like these 3 kind of the aspect ratios and these 3 scales, we are basically making the 9 anchor boxes, which are basically centered at each of the pixel. So if we are basically taking some kind of the n number of the pixels, then we are basically having the 9 times n the number of the candidate regions. So that's the basic ideas. So what we basically do is that for each of some kind of the local regions, we are basically taking the 9 anchor boxes, and then we basically predict the kind of the object needs, which is basically kind of score measuring about like how likely a object will be included and also basically bounded in the given the anchor box. So having this kind of the object needs these scores. So once we basically get this kind of the object needs these scores, which is basically sort of like classifying each of the anchor boxes, whether these will be really the bounded boxes for the objects or not, right? So once for some of the bounded boxes that are classified as kind of the bounded boxes for each of the objects, then now we can also predict some kind of the additional information like the classification scores and also the offsets of the bounded box, the center and the scales. And also here the key thing is that basically we are having the 2 parts of the prediction in the neural network. One is basically proposing the regions, which is basically actually predicting the object needs for each of the regions. And also the next part is basically getting some kind of classification of the scores and the bounded box, the center and the scale, the offsets. And also here the key idea is that we are also sharing the same feature map for both of the tasks to predict the object needs the scores, and also to get the classification of the scores. We are basically using the same feature map to get all this kind of information. So in this way, we can also save the time while basically getting some kind of the high accuracy in the 2D object detection by basically running the neural network only once for both of the tasks. So that's the very basic idea for the 2D object detection. And obviously here the output is basically getting the bounded boxes for each of the objects. And for the segmentation, basically we want to get not only the bounded boxes, but also some kind of the mask for each of the corresponding some kind of the objects. So what we can also do for the instance segmentation, here basically the thing is that for the object detection, we only get the 2D bounded boxes for the objects. But now we can also consider basically getting some kind of the foreground, the mask region for each of the corresponding the objects. And for that, what we can do is that we are simply adding the one more the module, which is basically getting some kind of the basically adding some kind of the fully convolutional neural net, which is getting some the per pixel the information in a way that for each of the region, now we are getting not only the classification discourse, but also getting some basically the per pixel the some kind of information in a way that we can basically also extract the foreground, the ground, the mask for each of the bounded box. So by just adding one more module, basically getting some kind of the foreground, the mask, we can also turn the object detection in neural network into the segmentation, the instance segmentation in the network. So this is the very basic idea in terms like how we can also make some kind of the 2D the object detection and also the segmentation the networks using the simple the convolution neural net. And obviously, there are some lots of the kind of the variance in terms of like replacing the convolutional neural net into the transformer or some other kind of the other the backbone the architectures. But having the region proposal basically, and also having this kind of the segmentation, the network is basically the very basic kind of the components in the all the to the detection and the segmentation the networks. Do you have any questions on this? Yeah, so please note that the basic idea for the 2D object detection, the segmentation is basically getting some kind of the region proposal. And then for each of the region, we are basically getting some kind of the classification discourse or some kind of the foreground, the mask in terms of getting some kind of the object information and also the segmentation information. So obviously here the question is that how are we gonna basically apply this kind of the idea for the 3D case as well? So we can also consider basically making some kind of the very similar the idea in terms of having some sort of the region proposal and also doing some kind of segmentation. And we can think about like three different approaches in terms of like how we're gonna like extend the idea of like 2D detection and the segmentation into the 3D case. Then obviously the simplest idea might be that we are just using the 3D convolutional neural network. So as we basically had the 2D convolutional neural network, we can also directly extend the idea by using the 3D convolutional neural network, which is basically exactly the same as like what we have done in the 2D case. So for the 3D case, we are also basically having some kind of the some proposals of the 3D bounding boxes. And then we also extract the features for each of the region and basically get some the classification scores and also some kind of the foreground, the mask the regions. So we can basically do the same thing using the 3D convolution neural network. But we also know the downsides of like this kind of approach, right? So what will be kind of the limitations if we just directly use the 3D convolution neural network? Second question. Yeah, so computation time basically also takes lots of the memory and the time. And also, as we also discussed in the previous lectures, like obviously using the 3D convolutional net is also very inefficient way to process all the 3D data, right? Because there will be lots of some kind of the empty space in the 3D space. So if you just directly apply the 3D convolutional neural network into the 2D the segmentation, the idea, then we're gonna see that it becomes like very inefficient the system in terms of that we are also running some kind of convolution in the empty space as well. So that's why we basically discuss the idea in terms of making the point net kind of architecture that can directly process the point cloud the representations. Actually, the other way around, not to use the 3D convolutional neural network, use some kind of the image-based some kind of ideas, because for many kind of the cases, for example, like for the outdoor scenes, actually we can treat all the 3D the data as kind of the 2D data in terms like having some kind of the bird eye views. For example, like if we have the top views of the from the sky to the ground, then we can basically treat all this kind of 3D information as kind of the 2D data. Then we can basically treat all the 3D information as kind of the 2D images and use the same 2D object detection, the segmentation, the network. So this is like one of the examples that we are basically treating all these 3D things like RGB, the colors plus the depths as kind of the full channel images from the bird eye view and running the same the 2D object detection, the segmentation, the architectures. Then also, what would be the downside of like this case? If we only just like treat everything as kind of the some 2.5D images. Yeah, so this basically cannot account for some kind of the occluded regions, right? So basically, this might basically work for some of the kind of the cases like like even like, for example, like political autonomous driving, it might be okay to basically see everything from the bird eye view. But if we basically like detect some of the objects in some basically some complex, for example, like some indoor scenes, there might be some of the objects that might be occluded if we see everything from the top view, right? So if we want to basically handle some more kind of the complex scenes with some more like the complicated the arrangement of the objects in the scene, basically just having the one view of the 3D things will be basically very limited in terms of basically detecting all the objects. So this might be only okay for some kind of the certain types of the scenes, like some kind of the outdoor scenes. So there are some kind of the extension of like this kind of idea, which is still kind of like leveraging some kind of the 2D segmentation or the object detection, the architectures, but basically having some not only the bold eye views, but for some kind of having some multiple views. So here basically the idea is that we are using some kind of the almost the same the architecture with the faster RCNN and the masked the RCNN. But the thing is that once we get some kind of the 2D proposal for each of the view of the 3D things, then for the segmentation and also the classification, we are not only basically just treating all the each of the region as kind of the 2D image, but actually we are taking the 3D point cloud, which is basically included in the 2D region. So we are now treating each of the 2D region not just into the 2D box, but as kind of the flusterstorm in the 3D space in terms of that we are basically now taking out some of the 3D point cloud inside each of the flusterstorm and then basically now using the point net to process that in terms of getting some kind of the foreground, the mask, and also getting some all the classification discourse. So this is kind of the interesting the case in terms of like making some kind of the combination of the mask of the RCNN and also the point net. Yeah, so there was the typo here. It should be mask RCNN here. Yeah, thanks. So yeah, this should be basically some kind of the interesting the idea in terms like we are making some the combination of the mask of the RCNN and also the point net in terms of that we are first getting the 2D proposals using the 2D convolutional neural network and then basically treating everything in the 2D mask as kind of some 3D thing. By just seeing the 2D mask as kind of the flusterstorm in the 3D space, and then using the point net to get the mask, the 3D mask, and also get the classification discourse. So this is also the simple the idea. But still the kind of the downside is that it's still having the 2D detector, which is still treating everything as kind of 2D, while we are basically having the full 3D information. What is flusterstorm? The flusterstorm is basically nothing but basically having this kind of the some truncated the rectangular the cone the shape on the you can see my mouse point. Yeah. So if you have basically 2D the region and if you basically shoot a ray from the 2D region into the 3D space, then you can see that actually the 2D box in the image can be basically extended into this kind of the truncated the rectangular the cone shape, right? So this basically the truncated the rectangular the cone shape will be basically the flusterstorm in the 3D space, and then now we can basically take out the point cloud in this kind of the shape, some kind of the bounded the flusterstorm, and then we basically the process the point cloud for each of the 2D region using the point net. So that's the basic idea. Still, this is kind of the case that we are basically going in the halfway to basically treating everything as kind of 3D. Still, the region, the proposal is basically done with some kind of the 2D detector. So how we can basically fully utilize all this 3D information for the segmentation is kind of the problem here. So what we want to achieve in this kind of the case for in terms of making the 3D, the object detection, the network, is that we want to make some kind of the efficient the architecture, which basically can process the point cloud information directly without using basically the 3D volume information in a way that we can avoid the cases that we are basically doing some kind of computation in the empty space. So that's basically the first thing that we want to achieve. And also the second thing is that we don't want to basically assume any kind of some sort of the canonical viewpoint in terms when basically treating processing all this 3D information. So instead of like picking some specific view to treat all these kind of 3D information, how we can basically just like utilize all the 3D information in a way that we can also handle some basically very complex the arrangement of the 3D objects. Might be also kind of the one thing. And also the other kind of thing is that we want to basically utilize the entire 3D information without basically having any kind of the dependencies in terms of like having some of the 2D image detectors. So that's kind of also one of the things that we want to do. So we are going to briefly discuss some of the ideas in terms of like how we can make the object, the detection, the network in the 3D space that basically satisfies all these kind of the constraints. And for that, basically, once we basically make any kind of the architecture for the 3D object detection, obviously we might need some kind of the benchmark to basically assess the quality of the segmentation. So for the 3D object detection and also the segmentation, the very typical the benchmark that many people they use is basically this ScanNet. This basically ScanNet is basically indoor scene the data set, which is also basically a real scene data set that are basically captured by some kind of the multi-view images, basically a video. So there are basically more or less like 1,500 indoor scenes that are also basically created by collecting 2.5 million the multi-view images. So this is kind of like quite a huge data set and also very complex data set. As you can see, there are kind of like lots of the objects that are basically arranged in a kind of complex way so that many of the objects cannot be detected if we see the scene from the top view, right? So that's basically why we cannot just directly use the bird's eye view kind of the base kind of the ideas in terms of using the 2D segmentation, the architectures. So this is basically the real case that we really need to use some kind of the 3D object detection and the segmentation, the networks. So you can actually check out the benchmark and also the state-of-the-art the methods and also their performance as well. So this is also slightly outdated kind of the graph. Actually, if you go to the website of ScanNet, you can check out the up-to-date the state-of-the-art kind of methods and also the performance as well. And as you can see, we start to see some kind of the big jump of the performance from the 2019 and 2020. And those are also the time that we start to see some kind of the new interesting ideas in terms of like how we're gonna basically make some kind of the 3D detection and the segmentation the architectures. So we're gonna briefly discuss some of the ideas today and also probably next week as well. So we're gonna briefly start to discuss the botnet the idea, which is about the object detection. So basically the goal of the botnet is that now we are taking a 3D point cloud as input. So whether we basically have some kind of the real scans or some kind of the reconstructed meshes, and even when we have some kind of nerve reconstruction of these scenes, we can basically convert everything into some kind of the point cloud. And we are assuming that basically this point cloud is basically the input. And given the point cloud, we are going to basically predict a set of all the bounding boxes, basically oriented bounding boxes in the 3D space with their semantic labels as well. So as kind of the output, we are going to basically get the position of the bounding box and also the scale of the bounding box and also the orientation and also the semantic labels as well. And basically here also we are getting the A model, the 3D oriented bounding boxes. And the meaning of the A model here is that while we might have some kind of the partial point cloud, we want to get the bounding boxes for the entire the objects. Right? So when we basically scan the real 3D scenes, there might be many kind of the cases that we are basically missing some of the regions because of the occlusions or some kind of the issues with the depth sensors. So we can assume that the input of the point cloud can have some kind of the partial information, basically missing information. But given the partial information, our goal is to basically get the bounded boxes only for not only for some kind of the partial observation of each of the objects, but we actually want to get the bounded box for the entire the objects. When you basically assume that the some of the missing areas will be basically filled with some kind of the complete objects. So that's basically what we want to do. And for that, basically, if we basically want to directly apply the idea of the mask RCNN, then what we can do? Then we can also try to somehow define some kind of the anchor boxes for each of the points and get some kind of the objectness discourse and also the classification discourse, right? So we can directly consider using some kind of the point net or some kind of the point net divariant in terms of like getting some kind of all the objectiveness scores and also the classification scores for the given the set of the anchor boxes that are defined for each of the points. So they can be very direct extensions. But can you basically imagine some of the kind of the downsides if we basically directly use the masked the RCNA idea here, the fast RCNA the idea here? What would be kind of the downside if we just directly use the point and the plus plus with some kind of the anchor boxes for each of the points? Question? Yeah, so actually what we need to see here is that we are now using a point cloud of the 3D the scenes, not the voxels. So the difference with the case of the fast RCNN and the hourly case is that in the fast RCNN, we are basically having all the pixels that are basically the elements of the 2D the grid, and then we are basically proposing some of the regions with anchor boxes with lots of the pixels there. And we can basically assume that most of the bounding boxes of the objects might be basically represented as kind of the anchor box of any of the pixels there. But here the thing is that we are basically using the pixels, the points of the point cloud, not the voxels in the 3D grid, which means that even when you basically populate all the anchor boxes based on the points of the point cloud, some of the bounding boxes of some of the objects may not be covered by our anchor the boxes. So for example, like this might be one of the examples that we want to basically have the bounding box, the 3D bounding box of the kind of the table in the scene. But basically, if we see each of the points of the given the table, all the points are basically very far from the center of the 3D bounding boxes. So which means that even when basically populate all the anchor boxes for each of the points in the table, those basically the set of the anchor boxes may not be basically aligned with the bounding box of the entire object. So that's kind of the problem when you basically have some kind of the point cloud instead of the 3D the voxels. So in the case that when you basically have the 3D voxels, then obviously the anchor boxes of some of the voxels near the center might be able to basically cover the entire bounding box of the table. But when you only have the samples of the points over the surface of the shape, the anchor boxes of the points may not be aligned with the bounding box of the entire object. Especially in the case that when the center of the object is really far from all the points of the surface of the shape. So this is kind of the issue, like in terms like when you directly apply the idea of the fast RCNN in the 3D case. So that's basically why we want to basically use some kind of the other idea, which is based on the Hopf transform. So let me briefly explain the idea of the Hopf transform, and before we go into that, I would like to also ask, like, how many of you are familiar with the Hopf transform or not? Have you heard about the Hopf transform before or not? No. Yes. Yeah. So this is like very fundamental, the idea in the computer vision. So it might be worth basically checking out the ideas of like this Hopf transform, which is basically used not only for the 3D segmentation and the object detection, but this is very the basic idea for many kind of the model estimation problems. So this is slightly off topic, but let's get into the model estimation. So let's think about the case that we're having a kind of like given set of the data points, and we want to fit a kind of the model into given the set of the data points. So what's the model in this case? Like, for example, like this is like one of the examples that we are having a set of the 2D points as the input, and we want to fit a line. That is basically somehow like, minimizing all the distance to all the 2D points. So how we can basically find the best model that basically best explains the given the data set. So this is kind of like one of the examples for the model estimation. And this can be used not only for fitting a line, but it can be used to basically fit a circle or basically fit some kind of the some cubes, other kind of things. So this is basically some very general problem in terms of that we are having a kind of a set of the data points and also the model that we want to fit. So given this kind of the set of the data points, probably with some kind of the noise and also the outliers, how it can fit the model that basically best explain the given set of the data is the model estimation problem. So there can be some bunch of the approaches to basically solve this problem. Obviously, the first idea might be linear regression. This is basically nothing but basically we are solving the basically the optimizing the problem in terms of like minimizing the distance from the estimated model to all the data points, right? So in the line fitting case, basically we can find a line which is basically minimizing the distance from all the points to the line. So that can be the easiest way, right? But the reason why people do not use this kind of the linear regression in the many cases is that, can you guess the reason? Like, what's the kind of downside of the linear regression for many of the cases? Yeah, so obviously the problem of the linear regression is that it will be kind of like very sensitive to the noise and the outliers. So as you have some kind of the outlier the points, it will affect a lot in terms of like finding the best model. So that's why basically also people come up with some kind of the different idea. So the idea is the rank set, which is also very common the idea in the computer vision. So what we do in the rank set case is that now we are not just directly optimizing, solving the optimization problem in terms of finding the best model, but what we do is that we are basically making some kind of the candidates for the models in a way that we are basically picking some of the data points here. So what we can see is that if we just like pick 2 points in the given the set of the points, then we can basically draw a line connecting these 2 points, right? So picking the 2 points is basically making some of the proposals of the model, right? So we can basically first randomly pick a pair of the points multiple times in a way that we can populate them in some kind of the candidates for the model. So basically, for the circle, basically we might need some like not only 2 points, but the 3 points, right? For the other kinds, the models, there might be some kind of the minimum number of the data points to define a single model. So in the line fitting case, we just need the 2 points to define a model, which is the line in this case, right? So we basically make lots of the candidates of the model by just picking the 2 points, and then now fit basically draw the line for each of the 2 points, and then measure the fitting error to all the other points. And then what we can do is that we can just like pick the best model, which is minimizing all the errors to all the other points. So this might be basically one of the examples that we are basically finding the best model that describes the best explains all the given the data set, even in the case that when there are lots of kind of the outliers. So this is also the very common idea that people are using in the many computer vision problems. But still kind of the downside is that this idea only works when still the number of the outlier is basically not too big. So if we start to have some kind of many of the outliers, like even more than the 50%, then even it will be really hard to basically find the best model even with these kind of rank ideas. For example, when we basically want to find not a single model, but basically the multiple models like this, So this is one of the examples that we want to find the multiple straight lines from the points that we basically highlighted with some edge detector. So the left one is basically the input, and the middle one is basically some of the outputs of the edge detection. Based on those kind of the points that are on the basically the edges of the images, we want to basically find all the straight lines, as you can see on the right-hand side. For those kind of the cases, for the points on the other lines, those points might be basically the outliers for the some certain the model, right? So for those kind of the cases that when you want to basically find some multiple the models, basically we need to have some kind of the better strategy in terms like finding some multiple models. So for that, what we can do is that we are basically using the idea of the Hopf transform. So the main idea of the Hopf transform is that it's the same in terms like we are basically randomly sampling the points. So as we have done in the RANZAC case, we also randomly sample a pair of the points in a way that we can also somehow like populate some kind of the candidates of the models, right? So we are basically drawing some multiple lines by just taking the 2 points. So you basically make a kind of the line by just picking the 2 points. Then we can see that at least like this line is basically explaining that specific the 2 points, right? But we also might want to see how many basically the points are basically explained by that model. But what we do is that instead of basically measuring all the defeating the errors, what we do is that we are treating the sample of the points, each sample of the points, as kind of like one vote for each of the line. So that's basically the basic idea. So once we basically sample a pair of the points in the given the point cloud, what we do is that sample becomes like one vote in the line parameter space. So basically we can parameterize the continuous space of the lines as kind of the, for example, having the parameters of the slope and the offset, right? So which means that any kind of line can be represented as basically offset and the slope. So in this 2D space, each of the sample of the 2 points becomes a vote, basically mapped to the one of the single point in the line parameter space, right? So what we can see on the left-hand side is that we are now picking the 2 points in the 2D space and making this line. And this line is basically mapped to a single point in the line parameter space. So basically, this is like another the 2D space, which is basically representing the line parameters. Like the one axis is for the slope, and the other axis is for the offset, right? So a line in the 2D space is now mapped to a single point in this space. And then we can basically collect lots of the votes in this line parameter space and see where all the votes are basically concentrated on. So this is like also one of the examples. Basically here we want to basically detect these 2 lines here. Then we are basically sampling the 2 random points over these lines, and then voting in the line parameter space by mapping the line in the 2D space into the line parameter space. The x-axis is the angles and the y-axis is the offset. Then we are basically having this kind of the votes in the line parameter space. And once we have all the kind of the votes, what we need to do is that we just need to see where basically the votes in the line parameter space are basically concentrated on. So what's the kind of the peak point of the votes? So that's basically what we are doing in the Hopf transform. Is this clear? The idea of the voting? So what you do is that in the left-hand side, let's say like the left side image is the input image, then we randomly sample the 2 points over the given the lines. And this will basically draw a line in the 2D space, right? And this will be also mapped to a single point in the line parameter space. So the line parameter space is basically having the x-axis, which is representing the slope of the line, and also the y-axis, which is representing the y-offset of the line, right? So we basically accumulate all the votes by just randomly taking all the samples, the 2 samples of the pair of the points, and then see where basically the votes are basically accumulated, concentrated. So you can see that this point on the mouse point and the other point here these might be some of the points that we are seeing some kind of the concentration of the votes in the line parameter space. So if we can basically find this kind of the peak points, then we can see that actually, yeah, there are basically two models that are basically explaining the entire data set. So that's the basic idea for the Hopf transform. Any questions on this? Yeah, so there can be some also a bunch of the ideas in terms like how we can basically find the peak points. So there are also kind of various kind of the ideas in terms of doing some kind of the mode seeking. One of the basic idea is also the mean shifted clustering, which is basically nothing but basically defining a kind of the probability distribution from the given the set of the votes, basically from the given set of the samples, by having some kind of a corner function. So as you can see here, what we are doing is that for each of the votes, for each of the sample point, we are kind of like sort of defining a kind of volume of the probability distribution in a way that having this kind of the distribution for each of the sample, which is typically defined as kind of the Gaussian like this. And then when you basically accumulate all this kind of sort of the volume of the probability distribution for all the given the points, then we're gonna see some kind of the distribution like this on the bottom side, having some kind of the distribution in the given kind of the space. And then now what we do is that once you also sample some kind of random points over the line, the parameter, the space, we are basically shifting each of the point into the basically the peak point in terms of running the gradient descent. So that's the basic idea. So this might be clear in this figure. So on the right-hand side here, what you can see is that we can see this kind of some sort of the slope of the probability distribution, the function over the space. Then what we do is that we are basically distributing some kind of random samples over the space, and then moving all the points over the kind of the peak point at each of the local region by in terms of running the gradient descent. So that's the basic idea. So how we can basically calculate all the gradient descent. So this is kind of like one specific examples that when we basically define the corner function like this, something like the Gaussian the distribution, if we basically run the gradient descent, then what we can see is that this becomes actually nothing, but actually we are taking some kind of the local neighbors for each of the sample, and then basically computing the mean for each of the local neighbors, and then moving the point into the mean of the local neighbors. So that's why this idea is called the mean shifted clustering. So basically, it turns out that at the end, what we can see is that this algorithm basically becomes that we are starting from some random points. And for each of the random points, we are basically taking some kind of the local neighbors and computing their basically the mean of the local neighbors, and then moving the points into the mean of the local neighbors. And if we basically repeat this process multiple times, then we're gonna see this kind of results that all the points are basically being converged into the peak point of basically given the probability distribution. So that's the basic idea of the mean shifted clustering, and also the other types of the mode seeking the algorithm can be basically used to find some kind of the peak point. It is clear. So this is like very general the idea that can be used for some kind of the model estimation in many kind of computer vision programs. And especially this kind of idea can be useful when you basically want to find not a single, but the multiple models at the same time using the given some kind of the data distribution. And also there are lots of kind of the applications in terms of like generalizing this idea for the multiple applications. One question, can you once more explain how it is related to the Hopf transform? Well, basically, this is the part of the Hopf transform, because what we need to do is that in the Hopf transform, we are basically sampling the points from the given the data points and map the model into the model the parameter space. And what we want to do is that we want to basically find some kind of the peak points here, which is basically representing one of the lines here, and the other peak is also finding the other line here, right? So given this kind of the distribution of the votes in the parameter space, how we can find the peaks is basically the question here, right? So for that, what we can do is that given this kind of set of the votes, we can basically run the mean shift the clustering the idea in terms of like basically shifting all the points into the local mean at each step. Then we can see that this kind of the shifting the process will be converged in terms of like we are finding this kind of the peak points. And then we can basically take this as kind of the some of the output the models that we want to find. And this will basically be drawn as kind of the line in the 2D space. It is clear? In the peak in the input image of how to transform a line. So basically the peak in the parameter space becomes a line in the image space. So this is like one example that the left in the is the input image, and the right is basically the visualization of the votes, which is also in the 2D space, but not the Euclidean 2D space. But this 2D image is basically representing the line parameter space. The x-axis is the slope of the line, and the y-axis represent the y-offset of the line. Make sense? Yeah. So what we do is that we sample the 2 points in the image space, make a line. This line will be mapped to the point in the parameter space. Once we accumulate all the votes in the parameter space, we run the mean shift clustering in the parameter space in terms of like finding the peaks. And these peaks point will be also mapped to the line again into the 2D space. So this is the basic idea of like applying the half transform the idea for the line detection. And this can be also used in the many other applications as well, right? So if we, for example, like if we can use this idea for the like, for example, like sphere detection in the 3D space, we are having these 3D points, want to basically fit some kind of the spheres. Then by basically taking like 3D samples in the 3D space, we can define a sphere and map this into some sphere parameter space and run the mean shift clustering and also go back to the 3D space and so on. Like so, yeah, it can be used in the many other kind of the applications. It is clear? Any questions? So actually, there are many kind of the generalized forms in terms of like how we apply this, the half transform in many other kind of the problems. So actually, there are also some of the examples in terms like applying this idea for the object detection as well. So this is also kind of the old work in terms of applying the half transform, the half voting in the object, to the object detection, which is not based on the neural net, but just using some kind of the simple idea. So what we can do is that we are first basically assuming that we're having some kind of the code book for the objects. So what we want to do is that we want to first basically sample some kind of extract some kind of the points of the interest. So having some kind of the key points in the 2D space. And then we are now taking some local patches for each of the point. And we basically want to use this kind of local patch as kind of the vote for the center of the objects. And for that, what we are doing is that we are having some kind of the code book of the local patches. So let's say we want to detect the cow in this image. Then we're gonna also assume that like we have some kind of lots of the reference images of the cows, right? So we have this kind of lots of the cow images, and we are doing the same thing, extracting some of the key points and then making the local patches, right? So when we basically compare the patches that we extracted from the input image and also the patches that we also extract from the reference images. So the patches in the reference images will be called the code book. So we are basically comparing the patch that we extracted with some of one of the items in the code book. If the cropped patch basically matches one of the item in the code book, then we can see that, yeah, this might be basically the patch that really belongs to the objects that we are having in the reference set, right? And also for all the patches in the reference set, we know where the center of the object is basically located with respect to basically the location of each of the patch, right? So if we have like this patch, then we can basically draw a vector to the center of the objects. And this might be basically some kind of the offset the vector from the local the patch to the center of the object, right? So based on this information, if we basically match the local patch in the input image with one of the patches in the reference set, we can vote for the center of the objects, right? So now we are having the parameter space, which becomes the center of the objects, and each of the local patches are basically voting to the center of the objects, right? So we can basically use the same idea in terms of basically accumulating all the votes for the centers of the objects, and then do some kind of the mean shifted clustering in terms of like collecting some kind of the peak points. Then we can see that now this kind of the peak points become the centers of the objects. But the thing is that our goal is not just to find the center of the objects. We want to find the entire segment, and these were the bounded boxes for the objects. Then what can you do? Can you guess? Like when you have this kind of the votes for the centers of the objects, then what can you do as kind of the next step? If we want to find the bounded boxes for the objects, once we get the center of the objects using the Hopf transform the idea, how can you also recover the bounded box information? Question? Actually, the idea is kind of like simple. So once we get the center of the objects, actually we have the information about like which patches basically contributed to make the peaks, right? So basically all the peaks are basically found by running some kind of the clustering, which means that we know which patches are basically associated with one of the votes that are basically included in the peak cluster, right? So we can basically do some kind of the back tracing for each of the peak the points. We can see like which votes are basically coming from the which patches. So in this way, from the peak point, we can go to the votes and also the local patches and see which local patches are basically associated with the peak. So by basically taking all these kind of set of the local patches that contributed to each of the peak, now we can also define the 2D bounded boxes as well. It's kind of the box that includes all the set of the votes, all the local patches. So that's the idea of the back tracing. Clear? So yeah, basically we want to apply this kind of the idea also for the not only for the 2D case, but also the 3D case as well. So this is basically the idea that we don't need to define any kind of the anchor boxes, but even when basically the center point is far from each of the points over the surface, we can directly apply this idea and effectively find all these 3D the bounded boxes. So what we want to do is that based on this idea, we want to find 3D bounded boxes using the point net or some kind of variant of the point net. So that's the architecture which is called the deep Hopf devoting. So this basically the pipeline is like complies with the main components. So what we do is that at the very beginning, we are basically using the point net the plus plus in terms of having some kind of seed points. So if you recall the point net the plus plus architecture, there's some kind of the hierarchy of the resolution of the points, right? So we are basically reducing the resolution of the points in a way that we can we are basically hierarchically basically merging some kind of local information. So as some kind of the intermediate level of the point net the plus plus, when you have some kind of the low resolution the point cloud with some kind of the seed points, now we are basically letting each of the seed point to have some kind of the vote for the center of the objects. So what we do is that for each of the seed point, we predict the point offset and also the feature offset that will basically represent the center of the object and also the feature of the object. So we can have the single vote for each of the seed point, or we can have some multiple votes for each of the seed point. So let's assume the simplest case, like having the single vote for each of the seed point. Make sense? So once you basically run the pointinity plus plus for each of the seed point, we are basically making the seed point to basically vote for like one single the object with the center and the feature. And getting the center and the feature points is kind of the offset here. And then what we need to do is that we need to do some kind of clustering, right? As we have done with the mean shifted clustering in the 2D case, we just need to do some kind of the clustering to find some kind of the peak points. Actually, we can use the mean shifted clustering here as well. But this idea, the framework, even using some like simpler the idea in terms like the things, this kind of clustering, which is like first doing some kind of the farthest point sampling. So farthest point sampling is basically nothing but basically iteratively adding some kind of points. Basically adding a new point, which is the farthest one from all the previously selected one. So once you basically have like one single point, and the next time you find the other point, which is has the farthest distance to the previous one. So once you have the 2 points, you also add the one more point, which is having the farthest point to any of these 2 points. So you can iterate this process in terms of like also finding some kind of the subset of the points, which is kind of like uniformly distributed over the given the set of the points. So once you basically have some kind of the seed points, using some using the farthest point sampling the idea, and then we can also aggregate the votes in some kind of certain radius. So you can see that basically all the votes are also 3D points in the 3D space. So once you basically have some kind of subset of the points, then we can basically aggregate the votes that are basically close to each other, close to the seed point by some kind of a radius desampling. And then we can aggregate all the information. So here what we can see is that we are not doing any kind of the back tracing. We just like aggregate all the votes. And the reason like why we are not basically using the back tracing is that here we basically want to get the A model the proposals. Which means that our goal is basically not to basically get the boxes for the partial observation, but we want to get the bounding box for the entire the 3D objects. So even when you get the local patch information that is contributing each of the peak point, this is basically not giving the information for the bounding box for the complete object, right? So that's basically why we are not basically applying the back tracing in this case. And we also want to get some kind of the additional information like the pools and the classes, like other kind of things. So for that, actually, we're just like aggregating all the pools without the back tracing. So basically, once we have some sort of the seed points and aggregate all the local defaults, and then the next step is basically proposing the bounding boxes and also the classification the scores. And the thing is that all the votes in this case are also the 3D points. So we can just treat them as kind of the 3D point cloud, which means that we can just directly use the pointinity architecture to get the bounding box information and also the classification scores for each of the clusters of the votes. So once we get basically the clusters of the votes, we just use the shared pointnet in terms of like getting the objectness, the score, and also the bounding box, the parameters, and also the semantic, the classification, the scores. So this is simply the idea. So yeah, you can basically check out all these some kind of qualitative results like this. So you can see that it's quite working well in terms of finding all the chairs in this kind of auditorium place. And also these are some of the examples, like also detecting all the furniture, like the chairs and the tables, all the things in the indoor scenes. Also the thing is that this is the case that we are not using any kind of the color or the image information. So even when you use only the geometry information without any using some color images, this still basically performs better. Some of the previous work using some kind of the fluster the idea or something else. So those are basically the cases that they are basically utilizing the 2D image detectors. But when you basically actually use some kind of run some kind of 3D segmentation, even without some color information, actually we can basically get some better results. So these are some of the results. And also the thing is that as we also discussed in the previous slide, without the voting, actually we can also directly run some kind of the reason proposal and the bounding box the information. But then actually, as I also mentioned, this might be kind of the not good because like we are not having using the solely the voxel information, but just the points information. So some of the bounding boxes of the objects, their the center might be really far from all the other points. For those kind of the cases, this kind of the direct the pipeline without the voting scheme may not be good in terms like properly predicting all the bounding boxes. So this is very interesting, the plot in terms of basically when we get some kind of some improvement of the accuracy when you use the voting idea. So here the blue dot basically indicates the performance gain when you use the voting idea. So as the blue dot is basically having the high the scores with in the y-axis, which means that we are basically achieving the performance gain when you use the voting scheme. And also the red points basically indicate the average distance from the object center to all the objects over the surface of the ship. So what we can see is that as the points over the surface are basically far from the center of the objects, we are getting basically the performance improvement using the voting scheme. So for some of the cases like the table and the bathtub and the dresser, those are some of the cases that the center of the objects might be actually far from some of the points in the objects. For those kind of cases, having the voting scheme can be more useful in terms of like improving the accuracy. And also there are some other evaluation studies as well. Yeah, and also this idea has been extended in terms like using both the 2D information and the 3D information there as well. So obviously, if we start to use also the 2D image information there as well, while also aggregating the 2D voting with the 3D voting, then we can also get some kind of the improvement in the accuracy. So the quick sum up is that this was basically the idea in terms like integrating the classical hub to transform the voting idea into some kind of end-to-end neural network in terms of having the three components. Like we are first having some kind of the voting from some kind of seed points, and then aggregating all the votings using some also kind of some merging the schemes. And then for each of some clusters of the votes, we are using the point net to basically get the final information for each of the instances. And we also have seen that like having this kind of voting scheme can be especially effective when the points or the kind of the objects are basically typically far from the center of the objects. So this was basically simply the idea. And also you can see that this kind of the voting scheme actually can be applied into some many other applications as well. So there are also some kind of the recent work about like using this kind of voting schemes for some kind of shape registration to align the basically 2-point clause, and also detecting the lines, and also to predict the pose of the objects, like some kind of rotation, the translation for the objects. This kind of the voting scheme can be used. So you can refer to this kind of the papers to see how this kind of voting idea has been applied to many kind of the neural net literatures. So this is the end of the idea for the object detection and the segmentation. Do you have any questions? So if you have any questions, please post the questions on the Slack. And don't forget that we're going to also have the office hour today at 7 p.m. in my office. So if you have any questions and if you want to get some feedback for your project, come join the office hour today. And then we're going to meet again on the Wednesday in our guest lecture. So I will see you on Wednesday. Thank you.